Okay, hello everyone. Today we will have a talk by Wolfgang Hönig, who's a postdoc from Caltech. So Wolfgang did his diploma at the University of Dresden. He then did a master thesis at the University of Southern California. And he did his PhD also in computer science at the University of Southern California. And right now he's a guest researcher at the California Institute of Technology. And yeah, I'm very happy that Wolfgang accepted our invitation, and I'm looking really forward to your talk. Thanks.
All right, thank you very much for the invite, Andreas and Mark. I'm really excited to give the talk here to Berlin. One thing that's very interesting is that at Caltech, robotics, at least in the group I was in aerospace. So I got to see kind of a little different side of robotics, and hopefully my talk today will kind of give you that view of that as well. So specifically, I will be talking about using function approximation for provably safe multi-robot motion coordination. And so my outline for today is that I first will jump into what do I mean by function approximation for multiple robots, kind of the key technology behind two papers. And then the main part of the talk will be those two papers, abbreviated GLAS and Neural Swarm. And at the end of the talk, I will conclude. So let's dive into function approximation for multiple robots. So if you have a multi-robot system, then typically that means you have robots that want to collaborate with each other in order to achieve a common goal. And that means their behavior ideally depends on the states that are observable or maybe not observable of the neighboring robots. Now in practice, if your robots are identical or homogeneous, you have the problem that you maybe not know how many robots are in your vicinity that you can observe. And you also have the problem that you don't really want to allocate an identity to each robot. So ideally, the behavior should be permutation invariant. So in this picture that you can see at the bottom, there's 3 quadrotors, and the quadrotors should do some task, and it should be independent their behavior in how I number those quadrotors. And so in learning, there's kind of common approaches on how to address this permutation invariance. And so maybe the most famous one is just regular CNNs, convolutional neural networks. But they require you to discretize as a space. And then it always becomes a difficult problem how to choose a reasonable discretization in this case. And maybe a little bit newer, but still used, are graph neural networks. And they typically also reason about communication directly. So you create a graph of robots that communicate with each other. And then when you deploy it, you also require this communication. So today, what I will use is a technique that I have not developed, but that was published at NeurIPS in 2017, which is called deep sets. And so the key idea or the key insight of the deep sets paper was that any continuous permutation invariant function f of x can be approximated as kind of this composition of two functions. And let me give you an example of what the paper used. So there the task was you have a set of input images. Each image has one digit. And your task is to just compute the numerical value of the sum of all the digits in each of the pictures. So for example, 5 plus 4 equals 9. Now, in the deep set approximation, the goal is that you have two neural networks, an inner network that learns the hidden state of each of the elements. So in this example, it would figure out that 5, the picture of 5, is the numerical value 5. And then you have a superposition of that hidden state. And of course, the hidden state in practice might be a higher dimension than your input space, which is not the case for the simple digits example, but in real world examples, that's how it would be. And then you have an outer function that basically learns the aggregation of the hidden state. And in this case, it's easy, it really just sums up. But for more complicated hidden states, that aggregation might be much more difficult. And by the way, you can always ask questions in the talk if you want to. We can handle it flexibly that way. All right, so that's the deep sets paper and the rough idea. And so now I will just jump into two topics where we have used that idea specifically for robotics. And the first paper was published at IEEE RALs this year. And that was joint work with Ben Riviere, who is a PhD student at Caltech, Yi-Sung Yu and Sunjo Chang, who are professors in computer science and aerospace, respectively. And the paper is called GLAS, which stands for Global to Local Autonomy Synthesis. And the idea is as follows. We noticed that for motion planning problems, there are kind of two techniques that people frequently use. So first one is centralized planning, and that's, by the way, something I did also during my PhD, where you have all the maps, the environment given, the robot properties given, and you just plan offline what all the robots should do. And the great thing is that you typically have good solution quality, sometimes even with nice theoretical guarantees. But the downside is that it can take a long time, so order of minutes, we're talking on a regular PC. And of course, it's centralized and you need full state information. So it's kind of impractical to operate in dynamic environments. And so the other typical solution are decentralized or reactive approaches. And so one of the most famous ones might be ORCA, which is optimal reciprocal collision avoidance. And that's very fast. It only needs local information, which is great, but it's incomplete. And so in this example, you can also see that some of the robots didn't really reach their goal because they kind of got stuck in this local minima in the obstacles because they do not have enough information of the environment. And so the key idea of this GLAS paper is basically to try to combine both in a learning framework. So we take our central planner and create lots of examples for different cases. And those examples are obviously in the full state space. So we can sample this full state space in order to create just a set of local observations. And for each observation, also our desired action. And then we can run imitation learning to just map our local observation to the desired action. And we will get a policy that is hopefully efficient at runtime and roughly maps out what the global planner has done initially. So I will visualize that a little bit with videos, and I hope that Zoom will show that nicely. So here are just some examples on the kinds of trajectories we generate. So we just create random obstacles, we randomly initialize start and goal positions, and then we have different numbers of robots in different environments. Now, when we extract local observations, all we do here is we basically sample the trajectories that we got for each robot. So if I have 4 robots, I get data for 4 robots even. And then we put an observation radius around it and just make sure that the observation only contains information that the robot can actually see. And that gives us a lot of data because we get data per trajectory. We can sample multiple points. And for each centralized planned example, depending on the number of robots, we also get more data that way. And then we use an imitation learning framework with the neural network architecture, of course, that uses the deep sets that I introduced earlier. And here we specifically use two types of deep sets. The first deep set just encodes the obstacles. So basically, the input set would be the relative position information of your obstacles. And the output would be some hidden state that we might or might not understand. And the second deep set is the neighboring deep set, and that simply encodes the same relative state information of all the other robots that are within your observation radius. And then we have another feed-forward neural network, Psi, and that network just aggregates all the information from the deep sets, the obstacle deep set and the neighbor deep set, and then also our goal information where we actually want to go. And then our output is the policy pi. So in principle, this policy would already work, but it wouldn't give us any guarantees. Like we could deploy it and it works, but sometimes the robots would crash, which is obviously not really what we want.
Can I actually interrupt? Sorry.
Of course.
Maybe not being like super expert in all of these many network architectures. So these deep sets, are they pre-trained in any manner, or is the whole architecture that you display here initialized randomly and only trained end to end?
Yes, only random initial guesses trained end to end, and they're really tiny. So each deep set, row, and phi networks just have a small feed forward layer. So it's not many layers.
But is there any way that is in the architecture that encodes that every deep set relates to one object or something? Is it clear that, I mean, one object is being fed into one of these deep set networks or something? Is this part of the architecture?
The only thing that's part of the architecture is that the number of elements in your set is variable. So if you have 3 neighbors, then your inner network is called 3 times. And the outer network is always just called once.
It is called 3 times, iterating over these neighbors.
Exactly. Like basically, I don't know if I have the equation again. But basically, if you look at the sum operation, it's kind of variable how many neighbors you have in that architecture. And that makes training a little bit tricky, like especially if you use batching, you have to make sure that you batch your data in a manner where you have the same number of neighbors. But otherwise, it's pretty easy to train those kind of things.
But you need to know, I mean, you need to know the number of neighbors that you have. You need to know the set as part of your training data so that they can iterate over that set and feed it to the deep set.
Exactly. Okay. Yeah, you need to know it, but then at runtime, it could be different.
Yes. That I get here. Yeah. But also at runtime, you need to have an agent or an obstacle detector and know, okay, here in that situation, we have 4 obstacles, and then we iterate over these 4 obstacles.
Exactly. Right? So in both works I present today, we abstract away perception. So we assume that we have some perception modules that gives us already position information.
Okay, cool. Thanks.
Okay, any other questions before I continue? All right, so let me recap. So we can train end to end, we get some policy, but the policy might or might not be safe in practice. And so one thing we really wanted to make sure is that whatever we design has a safety guarantee here. And so here we developed this differentiable safety module, which really is just from control theory, something similar to barrier functions, where the idea is, I think I have a separate slide, yep, where the idea is that we have multiple components. So one component, pi, is basically our learned or desired control. And then we have a safety barrier. And then we just have a convex combination of the two with that alpha, which is also a function, that basically makes sure that if we are in a somewhat safe areas, and we mostly use pi, so alpha will be close to 1. But if we are in an unsafe area, then alpha will go to 0, which means our safety barrier will kick in and decide what to do instead. And that kind of alpha is just important for very specific cases that you don't see often in practice, in particular kind of a gridlock where two robots run head-on-head towards each other. And so here I won't really go kind of into the proof. It's very involved from like a mathematical notation. But what I want to point out is that kind of the key idea is easy, and also the actual law itself is very easy, and in particular differentiable. So for example, this safety barrier B is kind of just looking like in a PID controller, the proportional gain. So you have a KP gain, and then you have this other term. And the other term is really just the relative position states from yourself towards your neighbors summed up, like in the lower equation. And then if you design all of that, then the safety proof it follows as a control theory idea using the Lyapunov method, and it just treats the learned function pi as a bounded disturbance. And that way kind of the standard methods still work to do the proof. And then in the paper, we also have the double integrator, but that just becomes somewhat ugly very quickly, so I don't really show it today. All right, and then we did some validation, of course. And so here are some examples. So we compared our central solution, Orca, which is that reactive state-of-the-art, what people typically do. Our own barrier, which is really just a safety barrier without where pi is just moving greedily towards the goal. And then we compare end-to-end learning versus learning without our safety barrier and see how the results are. And so let's look at some of the plots. So here we have the success rate. So let's first look at the top left plot. So we have on our x-axis the robot density. So it's the number of robots in our 8x8 meter field. And then the gray area on the right is the domain where we tested but did not have any training examples. And as you can see, for the two GLAS methods, both end-to-end and two-stage, they're actually really high on 100%. And success rate here really means there was no collision and you actually reached the goal within a time limit. And the barriers, like both our own design barrier and Orca, which is kind of a barrier but using a different mathematical formulation, also perform similar, but much worse compared to the learned solution. Similar results for the 20% obstacle case, although it's much more difficult to do planning in this case. And then one interesting thing is that the end-to-end learning did have a slightly better control effort compared to the two-stage learning. But for us, it was surprising that end-to-end learning did not really improve the success rate. Like, in fact, it even end-to-end, if you train end-to-end with the differential safety module, the success rate is slightly lower compared to the two-stage. And then for GLAS, another thing we were really excited about is just to analyze this trade-off between how much information you have. So in particular, if you increase your sensing radius, then you would expect at the very end that you can recover your centralized solution or close to the centralized solution, as long as you have enough data to train on it. And so what we did here is we trained our neural network with different quantities of data and also changed our observation sensing radius and increasing it slowly. And what we observed is, as one would expect, is if you have a very low sensing radius, then it's really difficult to recover good results. if you have a large sensing radius, you can get really good results, but only if you also have enough data. So if you're somehow limited by the amount of data that you can get, then there's an advantage in just artificially reducing your sensing radius, which basically reduces the domain you need to learn over.
Can I ask more questions about that plot?
Please.
I think for large data sets like 300. Oh, this is small. No, what is the 300?
It's an order.
Oh, it's not sorted.
Unfortunately, so it's, yeah, exactly. So so it's 30,000, 300,000, 3 million.
Oh, yeah, okay.
Yeah.
Was confusing. Okay, thanks.
Yeah, I think we got the same in the review. Maybe we have fixed it in the paper. I'm not sure. All right.
I have a very brief question about the plots 2 slides back. Sorry. I'm assuming that the centralized planner would have 100% success rate on all of the problems. Is that right?
Yes.
Okay. And do you know how the control effort there stacks up? Like just to have a comparison, is it lower in general? Should be, right?
Yeah, I actually don't know. It's a good question.
Okay.
But I would expect it to be lower. All right, we also implemented that, and that kind of plays into what Mark mentioned earlier, is that those deep sets are actually really small. They're much smaller than your CNNs or GNNs. And we implemented it on those tiny quadrotors, which just use a 32-bit microcontroller. And it just evaluates as a neural network, has our controller implemented, and I believe it runs it at something like 40 hertz or something. And that's a CPU that runs at less than 200 megahertz and has less than 200 kilobytes of RAM. So that's kind of like a big advantage over those other architectures that might be really big or very complicated to reduce in size in practice. And yeah, I mean, you can see it's like not perfect. It's like sometimes slow, but there's no collision and it eventually gets to the goal. All right, so that's basically all I wanted to say about the first line of work. And I would now move on to the second line of work, unless there are more questions. So the second line of work will also use deep sets, and it's called Neural Swarm, and that's a joint work with the same professors, Yi-Sung Yu and Sun-Jo Chang. And the first author was Guan Shi, who is another PhD student at Caltech. And that's work that has been published at ICRA this year. And so for this work, we were really interested in very close proximity flight. And that's kind of maybe an odd choice because it seems questionable where it's used. But in practice, actually, multi-rotors or quadrotors are used for things like collaborative inspection, fast exploration, and so on. And in those cases, it actually can be useful if you could control it to fly many of them very close together. Another example would be kind of multi-robot collaborative transport, where you have 2 quadrotors flying very close together. And so it turns out if you just do a fun experiment and try to fly 2 of them together, it works pretty well in almost all cases, except of this one case where you have 2 quadrotors flying on top of each other. And there's this effect called as a downwash effect, which basically literally the upper quadrotor takes the air away from the lower one. And then you see this kind of, try play it again. You kind of see this very large dip. And it's very brief, but still bad, of course, for trajectory tracking. And so we started out by just trying to measure how bad this effect is. And it turns out it is significant. So the quadrotors we use here are just 34 grams in weight. And then if you fly about half a meter on top of each other, you lose 8 grams of thrust. And that's actually a thrust that we could afford within like the limits of the motors. So technically, we should be able to compensate for it from the specs. What we didn't know from this experiment or from any related literature is what will happen if we have more than 2, and how can that even be modeled? So there's kind of some interesting models for a similar effect, like the ground effect, where it's somewhat analytical, but there's really nothing out there for like in-flight models. All right, so let's start a little bit of the dynamics. So the quadrotor is basically just following a normal rigid body dynamics. So we have an inertia matrix J, we have our angular velocity omega, and we have 2, okay, before I go to the next slide, we have 2 control inputs. It's kind of our torque and our external force. Both are created by the rotors, and depending on how fast you spin the rotors, you kind of can control that more or less directly. And now, when we fly quadrotors next to each other, there's an additional disturbance, which we can just model as residual dynamics. And of course, those functions are somewhat unknown. All we know is that they can somehow depend on our current state of all the robots, or maybe the environment, if there's obstacles like the ground effect, for example, potentially even our own control output. So that we don't really know. There's no good models. And so again, we use the deep sets, and we just assume that it should be permutation invariant because all the quadrotors are identical. So here, our set of neighbors is basically the relative state between robots. So for us, what we used was the relative position and relative velocity between robots that are somewhat nearby. And then we can try to approximate our residual force using a deep set. And yeah, just as a reminder, here's the idea is that we have 2 networks with separate weights. The inner network just has some sort of hidden state. And in our case, it's 40 dimensions. So it's definitely significantly higher than the relative state, which is just 6 dimensions. And then we have kind of a superposition of that hidden state. And then finally, we have an outer function that just estimates the residual force based on all the neighboring informations. And that one has another set of weights. Now, in order for training, we of course need data. So how do we get data here? It's actually fairly straightforward. So we do fly just random trajectories. We have to avoid that the robots crash into each other. And so we use the most basic approach that's out there, which is artificial potentials. It does require a lot of tuning, but eventually you get it to work. And then all you need to collect is your data from your accelerometer, which is on board, the orientation, which can come from your onboard state estimate or from a mocap, and then the motor forces, which you can get by just tracking your PWM signal and having a good accurate model of how that relates to the force. Once you have that, you can use your rigid body dynamics to directly compute FA, your residual dynamics. And then your data set just becomes the following. You have the set of relative states and the estimated residual force. And then, of course, we can again have different number of neighbors here, and so on. And then we can train it similar to the previous paper. Just to give you a visual how it looks like. So here we have kind of 2 quadrotors in a fairly small motion capture space, and they just fly to random positions, and the artificial potentials just always push them away from each other. And I think, oops. And then once you let's assume we can predict it somehow, and I will show you how the prediction looks like in a little bit. Once you predict it, you can actually add this additional FA term just as a feed-forward term into your position controller. And similar to before, because it's a deep set, it's actually very efficient. We can generate the C code for those deep sets, and then on our really tiny microcontroller, it just takes a few milliseconds to do it. And if you apply it, that's kind of how it looks like. So you see there's like nearly no error in C. You can see a little bit of jerk because it also gets an error in orientation, but it's definitely quantitatively significantly better. So here, for example, instead of 9 centimeters, it's just 2 centimeters, which is great.
Can I ask a question about that?
Please.
So the input to that prediction of the corrective term, wouldn't that require perception of where the others are? Okay.
Yes.
And so in the real experiments, do you have like a tracking device? So you have an exterior tracking of them?
Yeah, we use Viken motion capture system.
Okay.
And then I think we only get relative position information.
Yeah.
And the velocity is numerically estimated.
Okay. And then, so this is very technical, but then you actually have a Wi-Fi connection to these little things, or how do you send like the information to the controllers on board?
Yeah, so yeah, that's very technical, but basically those little things use a similar radio as like your wireless keyboard or remote would use. And there's broadcasting possible. So we broadcast the data out, and then every drone receives the position information of everyone. And then they can just filter who's the neighbor, who is myself. Yeah.
Cool.
Can I also quickly ask something? So the input to the network, that is just the relative position of all other quadrotors. It is not the velocity, or I don't know.
Yeah. It's a relative position and relative velocity.
Relative velocity as well. Okay.
Yes, but no relative orientation, because that would be really difficult to get. Okay. It would likely also work with relative position only, but presumably the accuracy would be slightly lower.
Yeah.
All right, and then so that was an example for 2. We continued with 3 and then 4. I think, yeah, that's the most we did for data collection. And then we kind of trained it with up to 4, and then we tested with 5. And that's the baseline. You see, it looks pretty terrible. And then if you apply the network, some of them still look bad, but that's actually because the motors cannot compensate anymore for the forces that are created. Like they're not powerful enough. But for the most part, the maximum or the worst case Z errors still reduced by a factor of 2 at least. And then we did a bunch of kind of fun experiments in the paper. Like one thing I really liked was just looking on generalization. So we trained with like little data and then tried with more robots. And so what kind of makes a lot of sense is that if you just train with 2, the neural network can definitely not figure out what to do with 3, 4, or 5, because the deep set itself doesn't have enough aggregation. But once you train with at least 3, it actually also works, or it shows definitely an improvement for even larger teams. And that's kind of similar to what we saw in GLAS, that to some extent it generalizes. Of course, you can't like go really high. Like if you train with 16 and test with the hundreds, it doesn't work. But train with 16 and then maybe try 25, 30, so it's fine. And that's just to give you another visual how it kind of looks like, the prediction versus what we measured. So here we just took separate data set and looked at when we fly it, how does the prediction compare to our onboard computed FA based on the IMU data. And you see that the original data is actually very, very noisy. And so the prediction is pretty good given that the data is so bad. So we're really happy about that. And then we can also visualize in those kind of heat maps how kind of FA looks like. And those diagrams are a little bit difficult to read. So basically, here's the idea is if we just look at the picture A of a 2 multi-rotor team, we have already a fixed rotor at, let's say, just height as 0, doesn't matter. So then if you would fly above it, then FA basically is 0. But if you would fly below it, let me see if my cursor works. Like if I fly here, FA is more or less 0. If I would place another quadrotor down here, then it gets pretty high, down to like up to like 12 grams or something if you're directly underneath. And then we can look at what happens. Oh, if we have like 3 quadrotors, we can also look what happens if one of them moves. It kind of gets this very interesting shape, which is cool. And it kind of validates other work people have done for the static case. Like we already knew that if you have 2 quadrotors in a static case, kind of a reasonable collision model is an ellipsoid. And that's kind of how this first one looks like. But we didn't really know how this dynamic case would look like, or the really large teams over here.
Maybe also a question to that. So some areas on the right, they are actually white, which seems like an upwash instead of a downwash. Is that true, or is it just an approximation error?
So that's actually super interesting. Like we tried to figure out with fluids people what's going on. And our current belief is that the neural network actually learned another residual dynamics that we didn't model, which is the modal delays. So for the small quadrotors, the modal delays are significant. And so we didn't only learn the immediate impact of kind of the neighborhood between the robots, but we also learned the effect of the modal delay here, which would be an upwash. And we have currently submitted a journal paper where we explicitly model the modal delay, and actually the white things go away.
I have another question. You just mentioned briefly that you talked about, or you looked at the plots with fluid people as well. I don't know the accuracy, but it should be possible to get similar graphs out of, well, fluid simulation, right? Do they look like, I don't know if you talked about them, did you think about something like that? And would they look similar?
That's an excellent question. We didn't get so far that they would run simulations for us, but I think it would be super interesting to compare that. From what I know from kind of fluid dynamic simulations is that they have a large margin of error. So in practice, like companies like Boeing, for example, still do a lot of wind tunnel tests because their simulation software is not that accurate.
Did you think about doing wind tunnel tests?
Yeah, not yet, but that would be interesting too.
Thanks.
All right, so what I, again, didn't talk much about yet is the theoretical guarantees. And so, of course, if we just plug in our neural network into our controller, that seems like a dangerous game to play. And so in particular, the challenge here is that the controller now directly relies or uses the neural network output. And so in order to still guarantee some stability, we have to look at 2 things. First, how does the neural network behave for unseen data? And that's something that I guess is studied a lot in the machine learning community, both empirically and theoretically, given how much data you need to get small approximation errors. But the second problem that we were really worried about is oscillations. Because the stability proofs always just give you a convergence rate. So at a certain rate, you will converge to your desired state. But if your desired state has high frequency oscillations, or your FA has high frequency oscillations, then your convergence rate doesn't help you because you will never converge fast enough compared to those oscillations. So you really need to make sure that you keep your oscillations as low as possible. And thus turns out that for learning, you can use a technique called spectral normalization that has another nice side effect, which is that it works great with noisy data. And you saw how noisy our data is. And so actually in the paper, there's again a fairly formal proof that shows exponential convergence. And I just want to quickly show you what it depends on. So that's kind of the convergence rate. And so it depends on your Lipschitz constant, which is the constant you give as input to your spectral normalization. It depends on the approximation error of your neural network, which depends on how much data you used and how large your domain is that you're interested in. And of course, it depends also on your control gains and your smoothness of the control, which is kind of typical for those kind of convergence rates. All right, so let me conclude and then talk briefly about some future work. So functional approximation, or of course learning, can be used both to learn local policies and residual dynamics. And if you take ideas from, let's say, traditional control or planning, then and combine it in an intelligent way with learning, then you can still retain theoretical guarantees. And then at the end, you get controllers or planning solutions that are decentralized and also computationally very efficient to evaluate down to the point that it works on a tiny quadrotor. Now, we also have some ongoing work, of course, which I won't have time to talk in detail. But so for kind of GLAS, we're looking at extensions for the adversarial setting and also to use the policies in a good way for more traditional, longer term, non-reactive motion planning. And for NeuralSwarm, we actually just submitted to TRO NeuralSwarm 2, which actually has some really nice theory on heterogeneous deep sets, including a representation theorem that shows that our deep set formulation can deal with heterogeneous teams with any kind of heterogeneous permutation invariant set. We also show how to actually use FA itself during motion planning, which is very challenging because there's this coupling between the robots. And I already mentioned we have this motor delay compensation, both in our baseline and in our own controller, which makes all the experimental results much more compelling, actually. And with that, I would like to thank my collaborators, Ben, Guania, Yisong, and Sunjo. And you can use our technology with the Crazy Swarm to get fun demos like this one in the video. And I'm happy to take any more questions. And if you can think about something, not now, but later, I'm always happy to answer emails as well. Thank you.
Thank you.